Overloads serve a vital purpose in electrical systems, ensuring the safety and longevity of motors and other equipment. When dealing with a roto-phase converter, the placement of overload protection becomes a critical consideration. The primary objective is to protect the motor on the single-phase side of the roto-phase. Therefore, overload should be placed before the roto-phase converter. This configuration ensures that the motor is adequately protected from overload conditions that may arise in the single-phase input. An overload condition occurs when a motor draws excessive current for an extended period. This can lead to overheating, insulation breakdown, and ultimately, motor failure. Overloads are designed to detect these excessive current draws and interrupt the circuit, preventing damage to the motor. By placing the overload protection before the roto-phase, any overload on the single-phase side will be detected and the circuit will be interrupted, protecting the motor. Now, let's delve into the reasoning behind this placement and the potential consequences of alternative configurations. If overloads were placed only after the roto-phase, they would primarily protect the three-phase equipment connected to the output of the roto-phase. While protecting the three-phase equipment is important, it does not address the risk of overload on the single-phase motor driving the roto-phase. A single-phase motor driving a roto-phase converter can experience overload due to several factors. One factor is excessive load demand on the three-phase side. If the connected three-phase equipment draws more power than the roto-phase is designed to handle, the motor will be overloaded. Another factor is voltage fluctuations on the single-phase input. Low voltage can cause the motor to draw more current to maintain its output, leading to an overload condition. Furthermore, mechanical issues within the roto-phase itself can also cause the motor to overload. By placing the overloads before the roto-phase, the motor is protected from all these potential overload scenarios. Consider a scenario where the three-phase equipment connected to the roto-phase experiences a fault, such as a short circuit. This fault would cause a sudden and significant increase in current draw on the three-phase side. If the overloads were only placed after the roto-phase, they would eventually trip and protect the three-phase equipment. However, during the time it takes for the overloads to trip, the single-phase motor driving the roto-phase would be subjected to extreme overload, potentially causing severe damage or failure. By placing the overloads before the roto-phase, the motor is immediately protected from the excessive current draw caused by the fault on the three-phase side. The overloads will trip, interrupting the circuit and preventing damage to the motor. It is also important to consider the sizing of the overloads. The overload should be sized appropriately for the full load amps of the motor. The full load amps can be found on the motor's nameplate. The overload should be selected to trip at a current slightly above the full load amps, but below the motor's maximum allowable current. The National Electrical Code, or NEC, provides guidelines for selecting and sizing overloads. Refer to NEC Table 430.52 for the maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices. NEC Article 430 covers motors, motor circuits, and controllers. This article provides detailed requirements for motor protection, including overload protection. It is essential to consult the NEC and follow its guidelines to ensure that the overload protection is properly installed and sized. In addition to the placement and sizing of overloads, it is also important to consider the type of overload protection used. There are two main types of overloads: thermal overloads and magnetic overloads. Thermal overloads use a bimetallic strip or a melt-in alloy to detect overcurrent. When the current exceeds the overload's rating, the bimetallic strip bends or the melting alloy melts, tripping the overload. Magnetic overloads use an electromagnet to detect overcurrent. When the current exceeds the overload's rating, the electromagnet trips the overload. Thermal overloads are generally more accurate and reliable than magnetic overloads. They are also less susceptible to nuisance tripping. However, thermal overloads can be slower to trip than magnetic overloads. Magnetic overloads are generally faster to trip than thermal overloads. However, they are also more susceptible to nuisance tripping. Choice between thermal and magnetic overloads depends on the specific application and the desired level of protection. For most motor protection applications, thermal overloads are the preferred choice. They provide a good balance of accuracy, reliability, and speed. When installing overloads, it is important to follow the manufacturer's instructions. The instructions will provide detailed information on how to install and wire the overloads properly. It is also important to ensure that the overloads are properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. Furthermore, regular inspection and testing of overloads is crucial for ensuring their proper functioning. Over time, overloads can become damaged or worn out. Regular inspection can help to identify these problems before they lead to motor failure. Testing can verify that the overloads are tripping at the correct current and that they are functioning properly. In summary, placing overloads before the roto-phase converter is essential for protecting the motor on the single-phase side. This configuration ensures that the motor is protected from overload conditions that may arise due to excessive load demand, voltage fluctuations, or mechanical issues within the roto-phase. When selecting and sizing overloads, it is important to consult the NEC and follow its guidelines. Regular inspection and testing of overloads is also crucial for ensuring their proper functioning. By following these guidelines, you can ensure that your motors and equipment are adequately protected from overload conditions. Let's now consider some specific examples to further illustrate the importance of proper overload placement. Imagine a scenario where a woodworking shop uses a roto-phase converter to power a three-phase table saw. The table saw is used frequently throughout the day, and occasionally the operator pushes the saw too hard, causing it to draw excessive current. If the overloads were only placed after the roto-phase, the motor driving the roto-phase would be subjected to these occasional overloads. Over time, these overloads could damage the motor, leading to premature failure. By placing the overloads before the roto-phase, the motor is protected from these occasional overloads. The overloads will trip, interrupting the circuit and preventing damage to the motor. In another scenario, consider a manufacturing plant that uses a roto-phase converter to power a three-phase air compressor. The air compressor is used to supply compressed air to various machines throughout the plant. One day, a leak develops in the air compressor's air lines. This leak causes the air compressor to run continuously, drawing excessive current. If the overloads were only placed after the rotor phase, the motor driving the rotor phase would be subjected to this continuous overload. This continuous overload could quickly overheat the motor, leading to failure. By placing the overloads before the rotor phase, the motor is protected from this continuous overload. The overloads will trip, interrupting the circuit and preventing damage to the motor. These examples illustrate the importance of placing overloads before the roto-phase converter to protect the motor on the single-phase side. This configuration ensures that the motor is protected from overload conditions that may arise due to various factors. When designing and installing electrical systems with roto-phase converters, it is crucial to prioritize motor protection. Overload protection is a critical component of motor protection. By placing the overloads correctly, you can significantly reduce the risk of motor failure and ensure the reliable operation of your equipment. Now let's delve deeper into the technical aspects of overload protection and the specific considerations for rotor-phase converters. The NEC defines an overload as the operation of equipment in excess of normal, full load rating, or of a conductor in excess of rated ampacity that, when it persists for a sufficient length of time, would cause damage or dangerous overheating. It does not include short circuits or ground faults. Overload protection devices are designed to protect motors and conductors from overloads, but they are not intended to protect against short circuits or ground faults. Short circuit and ground fault protection are provided by separate devices, such as circuit breakers or fuses. The primary function of an overload protection device is to protect the motor from overheating due to excessive current draw. When a motor is overloaded, it draws more current than its rated full load amps. This excessive current causes the motor windings to heat up. If the motor is allowed to operate in this overloaded condition for an extended period, the insulation on the motor windings will break down, leading to motor failure. Overload protection devices are designed to trip and interrupt the circuit before the motor windings reach a critical temperature. There are several factors that can cause a motor to overload. One factor is excessive mechanical load. If the motor is driving a load that is too heavy, it will draw more current to try to maintain its speed. Another factor is low voltage. If the voltage supplied to the motor is too low, the motor will draw more current to produce the same amount of power. A third factor is high ambient temperature. If the motor is operating in a hot environment, it will have a harder time dissipating heat, which can lead to overheating. The selection of the appropriate overload protection device is critical for ensuring motor protection. The overload protection device should be sized to trip at a current slightly above the motor's full load amps, but below the motor's maximum allowable current. The NEC provides detailed guidelines for selecting and sizing overload protection devices. The NEC requires that overload protection devices be sized no larger than 125% of the motor's full load current rating for motors with a service factor of 1.15 or greater, or with a temperature rise of 40 degrees Celsius or less. For motors with a service factor of 1.0 or with a temperature rise greater than 40 degrees Celsius, the overload protection device must be sized no larger than 115% of the motor's full load current rating. In addition to the sizing requirements, the NEC also specifies the type of overload protection device that must be used. The NEC requires that motors be protected by either thermal overloads or inverse time circuit breakers. Thermal overloads are the most common type of overload protection device used for motors. Thermal overloads use a bimetallic strip or a melting alloy to detect overcurrent. When the current exceeds the overload's rating, the bimetallic strip bends or the melting alloy melts, tripping the overload. Inverse time circuit breakers are another type of overload protection device that can be used for motors. Inverse time circuit breakers trip faster as the current increases. This characteristic makes them well suited for protecting motors from overloads. When using a roto-phase converter, it is important to consider the specific characteristics of the converter when selecting and sizing overload protection devices. Roto-phase converters can generate harmonic currents, which can affect the performance of overload protection devices. Harmonic currents are currents that are multiples of the fundamental frequency of the power system. These currents can cause overload protection devices to trip prematurely or to fail to trip when they should. To mitigate the effects of harmonic currents, it is important to use overload protection devices that are designed to be immune to harmonics. These devices typically use true root mean square sensing to accurately measure the current, even in the presence of harmonic currents. It is also important to ensure that the wiring and grounding of the roto-phase converter system are properly installed. Proper wiring and grounding can help to reduce the levels of harmonic currents in the system. In addition to overload protection, it is also important to provide short circuit and ground fault protection for the motor and the roto-phase converter system. Short circuit and ground fault protection devices are designed to trip quickly in the event of a short circuit or a ground fault. These devices protect against severe overcurrents that can cause significant damage to equipment and pose a safety hazard. Short circuit and ground fault protection is typically provided by circuit breakers or fuses. The size of the circuit breaker or fuse should be selected based on the ampacity of the conductors and the rating of the equipment being protected. The NEC provides detailed guidelines for selecting and sizing short circuit and ground fault protection devices. When installing overload protection devices and short circuit and ground fault protection devices, it is important to follow the manufacturer's instructions and all applicable codes and standards. Proper installation is essential for ensuring that the devices function properly and provide the intended level of protection. Regular inspection and testing of overload protection devices and short circuit and ground fault protection devices is also important. These devices can degrade over time due to environmental factors or repeated tripping. Regular inspection and testing can help to identify devices that are no longer functioning properly and need to be replaced. In conclusion, placing overloads before the rotor phase is crucial to protect the motor from single-phase overload issues.